What is convolution? It is a mathematical operation that blends two functions to create a third, where one function slides over the other at each position. A good visual example is to use die. Here we have two die, each with their faces having specific chances of appearing face up. What we'll be calculating is the chance that their faces sum to a specific number. This would be the equation for that, which will explain how it works later on in the video. But it is essentially the equation that represents what we will be doing with the numbers of the die. First, we have to flip one of them over and align their first numbers. We multiply the a and b values to get the chance that the die's face is summed to 2. In this case, a1 times b1 is the chance that the die's face is summed to 2. Then we move it over once, multiply the a and b values above and below, then add them together. Here we get the chance that they sum to 3. You can repeat this for 4 and all the way until you get to 12, which is the highest value that it can sum to on regular die. This process can also be used with the numbers you were given in MATLAB. You multiply the first value, slide it over, multiply, add together, repeat until you get to the end. However, since we're using a repeating sequence there, it actually ends up repeating the xn values over and over and over again. So instead of looking like this, when we get to the end, it actually looks like this. And this is why we add the 3 zeros, because when we add the 3 zeros, it cancels out these numbers and gets us exactly what we're looking for, which is the same value as the convolution function in MATLAB.
In the world of convolution, a simple real-world example would be sunlight shining through a window. While there is not much sunlight now, we can still use the normal natural light coming from the fact that it is daytime. So in this scenario, the daylight or the sunlight is what's known as x of n. It is the input signal. And the input signal is then filtered or distributed by the window, whether that be through the pattern or the fact that it's genuinely filthy. And that light now gets distorted by the filter. Another way that this could be demonstrated is by closing one of the blinds. For example, if I were to do that, the light becomes filtered further.
Whoa.
This is an example of changing my h of n value. And the light reflecting on top of an area such as this counter right here, this is your output. This is your y of n. So to recap, daylight, x of n, filter, such as the window, the absolute filth, or a window blind, are your h of n, and what comes through is your output, your y of n, which is the light that you can see on the table.
I'm going to be going over convolution of light in a time domain in terms of hardware. So basically, we're going to start off here with the big shift. And basically, these are two diagrams here talking about what we call a tap delay line. This is ultimately a simpler one in a mathematical sense, and this is one in terms of a hardware sense that you'll see with a in terms of like circuits and just data transfers and diagrams. So in hardware, convolution is almost always implemented as what we call a finite impulse response filter. And the standard hardware structure for this is called a tap delay line, as we can see here. This is a sliding window. We'll be going over this in the next few slides. But yeah, this is basically what we're going to be getting into. So it's called the shift registers. And basically, this is an example of what we just went over tap delay line. So as we can see, imagine the window here is made of several panes of glass, and as an input, let's say this pink square here, as input hits the pane, the ray that was initially hit moves to the second pane, and then keeps going in succession and transfers data. So we can see this here. It causes a delay, which is why it's called a 1 clock cycle delay, and we use this symbol z to the -1 here. But ultimately, these delay lines transfer data over and keep it going in succession to get an output given any end. And this is just a real-world example of a shift register. So here, another thing here we have is the window pattern or multipliers, and at every pane basically, and these are like the squares I just brought up earlier, the z to the -1s, there's a multiplier attached. And these multipliers here, they multiply the signal given a coefficient. If the coefficient's too low, the glass is going to be dark. The glass is like this red border here. it's going to block the signal. So you can't reach the output here on the cell. If it's around 1, the glass is going to be clear and the signal will pass to get to the output. Here, this is the floor pattern, which is basically the floor of these squares here. And basically, when light is passing through a window pane, for example, it hits the floor at the same time. The brightness on the floor is the sum of all those individual rays. So this is just a more advanced version of these squares here. And these are the output squares that are added together given an input. So this is just a more sophisticated version of that. And we wire the output of every multiplier, like I just showed you, into a giant addition tree here. This is and ultimately you can add multiple outputs together to get a wired output. And this physically creates the sigma symbol in the equation that we were given, as you can see here, because it's the summation of all the outputs. Last but not least, we have the engine, and the engine basically it not only multiplies but also adds in a single clock cycle. And it just does more with less, like it does more with less basically. And it's a key component of the whole tap delay line system and helps with convolution a lot.
You're probably wondering, what is the simulation actually showing? What is the filter actually doing? Well, here's a visual representation of the numbers flowing through the chart. The zeros right here are just placeholders as the numbers slide through, but you can see the ones coming from the X of n, one goes down, one goes and gets paused by the delay block. And then you multiply the ones, then you go down, the twos come in, the ones go over, one goes down, one stopped, 1, 2 goes down, one stopped, multiplied by the gain blocks, added together, all the way to the end, 4. Again, add the 1, all the way over, same thing, next step. Now the zeros that we've added are coming in, so the first value is now 0, add all the other ones, 3, again, until the end, where you get your 1, 4, 8, 8, 3, -2, -1 values.
This is convolution code to hardware. So with our convolution, we have an input signal and a filter that is multiplied onto the input signal, and then we have a summation over the number of iterations that we have to do, which will yield an output signal. So in MATLAB, convolution is really easy to do. We just need an input signal, or X of n, and the filter, H of n, and we can use this convolution function, which will give us our output, y in our case, and we can transpose y to get a column. So this is our stem plot of our input, but for Simulink we have to add some zeros on there to basically make this 1 from the filter line up with this -1 from the input signal, so that these zeros take care of these on the last step. So our filter is just a model of delays and gains and adders that are basically the convolution equation that can actually run on hardware. So we have our input signal that will run through this tap, and then it will be multiplied, and then it'll move to an adder. And then we'll go to the next value that we multiplied onto the filter, it will move to the adder, and then that will happen for every iteration until we have our output signal. And again, we have our input that runs to here in our filter, it runs through the filter, gives us an output signal. And then this is our output signal with the stem plot. So it's a little condensed here on the x-axis because this graph repeats, but it was just MATLAB being MATLAB. Rodney told us not to worry about it so much. But we can see that it's longer than the input. The input is only 4. It's just 1, 2, 1, -1, and then the zeros that fill it. So it's the length of the input plus the filter minus 1. So it should be 8 minus 1. And here we have 1, 2, 3, 4, 5, 6, 7. So we're good. And then going from math to an algorithm to model to hardware, we have our math again, we have our input and then the filter, and the filter is 4 components long, so we have 4 gains, and then the summation across every iteration. And then we can move to the model, which just takes an input, runs through the filter, gives us an output, and then this can be broken off into an FPGA or a DSP, depending on whatever your project needs. And then, so as I said, it could be broken off onto physical hardware, not very complicated. Delays would just be registers on an FPGA, gains would be multipliers, and adders would be an adder tree.